Okay, so thank you, Simon and the organizer, for providing me this opportunity. Yeah, it's a great honor, yeah, because I'm just a local student. So I think today I'd like to share, well, not research finding, but the journey of our research. So let's begin. As an introduction of my topic, let's consider a very traditional packing problem. It's honeycomb contraction, which is finding the least parameter partition of the plane into regions of equal area. And in this problem, we have three constraints and regions of equal area, infinite regions, and no boundaries. When relax the three constraints, we may get various related problem. And we can see if we relaxing the last two constraints, lead us to the least parameter partition of the disk in a monodisperse system, which I will introduce first. And then relaxing the first constraint, and we will explore the situation in a bidisperse system. So when n is less than 3 or equal to 3, the optimal solution for the least parameter partition of a disk into regions of equal area seems quite intuitive. For n equals to 1, it's just a circle. And for n equals to 2, cutting the disk in half. And when n for 3, it is mathematically proven. For the cases ranging n ranging from 4 to 43, some numerical construction solutions have been provided. The following diagram shows these partitions. The colored regions are considered topological defect, and it is qualified using a charge number, which is 5 minus n. N is the edge or the number of the edge. On the periphery, it's 5 minus n, and in the bulk, it's 6 minus n. And throughout the talk, I will mark regions with Q larger than 0 as red and Q less than 0 as blue. Just like the hard sphere packing, we also met the magic number cluster or the hexagonal number cluster, which we can see when n equals to 7 or 19 or 37. These patterns has the fewest topology defect and the symmetry, the best symmetry. And we can also find patterns with five-fold symmetry. There are some examples, maybe n equals to 16 or n equals to 31. And in most other partitions, topological defects are generally evenly distributed along the periphery, and with at most one pair of topological additional topological defects. And let me see how are these partitions obtained. We primarily use the surface law to perform our parameter optimization. Yeah, the surface law is a good tool, but it requires a topological structure as input. Also called, you can you can call this initial guess. But the initial guess is very important because the surface volvo itself is hard to perform some global operations. To obtain a reasonable topological structure, a path previously used by other researchers involved generating uniformly distributed seed point using a particle system with a long-range repulsion, and then obtain the topological structure through Voronoi partition. The question is whether this is the best path or which long-range repulsion works best is still unclear. Yeah, we may use a short-range repulsion system also, but currently we primarily use the column and log form of the repulsive potential. Yeah, regarding to perimeter optimization in the surface volvo, it's important to note that the topological structure is generally not likely to be optimal. We still need some local search option to find possible optimal solutions. For the disk packing problem, the optimal for the optimal the operation is similar to the T1 transition in the form. In surface volvo, it is done using both T1 transitions. The following figure shows that starting from the topological structure and performing one T1 transition, we can obtain the current optimal condition solution, indicating that it is a good topological structure. And what's the situation for the least parameter partition of a disk into two different areas? Some research has also provided conjectured solutions when n is less than or equal to 10, where they consider half of the regions are small and half as large. But the figure below shows that the least parameter partition for n equals to 10 as the error ratio changes. They used scaled perimeter to make it easier to distinguish the perimeter difference between partitions, as the actual perimeter difference are quite small. Now, here we show all the proposed possible candidate solution. Qualitatively, when the error ratio is small, regions of different area tend to cluster. Whereas when the error ratio is large, it seems that small regions are separated by large ones, so making it more mixed. Okay, similarly, they use surface volvo for optimization, and so a topological structure is needed as input. Here we show another way to obtain the topological structure. It can be imagined that when n is quite small, or possible topological structure can be enumerated. Researchers enumerated all possible three connected single cubic graph, which have direct correspondence with partitions. This method ensures that we explore all possible structures, but the drawback is also evident. When n is relatively large, the number of enumeration grows exponentially, making computational simulation too resource intensive. Okay, so we want to further explore the bidispersed partition of the disk. So we should rethink our research approach. Clearly, enumeration is no longer feasible. So perhaps combining the seed point with Voronoi partition can still provide good topological structure, while incorporation area swap during parameter optimization to enhance global search capabilities. This may be a feasible path. We hope that a good topological structure has a significant chance of being near the global minimum. So we can find the optimal candidate with just a few local or non-local operation. And here comes the question how to generate seed point. It's naturally introducing biodispers into the particle system. Yeah, that resulting two types of particles. This adds 5 additional parameters to the system to charge Q small and Q large, and to particle mass, and large and small, and the ratio of the number of different particles. We choose to fix one type of the particles Q and M to 1, and varying the other type of Q and M. So we now have 3 adjustable parameters. Okay, so let me reorganize the research method into 2 steps. First, generating random point, and use the global optimal algorithm Bayesian hopping to obtain seed points. And then use Voronoi partition to convert these seed points into a topological structure, which serve as input for surface evolver. Finally, use area swap and the T1 transition within surface evolver, along with simulate annealing algorithm to obtain candidate solutions. Yeah, as an initial exploration, we just fixed area ratio equals to 1.4, and still focus on partitions with half large and half small regions. In this case, only Q large and M large are variable in the particle system. We find that for all n small less than 10 or equals to 10 partitions, the particle system can directly provide topological structure for the candidate solution. We can observe the parameter range of Q and M that give good topological structures that reviews their cluster along the diagonal. So this makes sense because in a biodispersed particle system, having either parameter Q or M relatively large lead to the aggregation of different type of particles. This is a single illustration of this phenomenon. And that result in Voronoi partitions that are quite rare in the context of disk partition problem. Continue to explore cases when n large than 10, we find it challenging for seed points to directly provide the topological structure of the optimal candidate solution. In such cases, we hope that the topological structure is at least close to the optimal candidate solution. For n equals to 20, starting from a certain topological structure, stimulate annealing and fast annealing. Here, fast annealing refer to temperature dropping to 0 in the algorithm. The both algorithms both converge to the same minimum value. indicating that the topological structure is sufficiently close to the candidate solution. I think it's quite promising. The element showed at the left column is how the small region distribution and the topological defect change with the in the simulation process. And here I present some candidate solution for the least parameter partition of the disk in a bi-dispersed system. I think it's a relatively rough research project, so it's just for demonstration. And I do not think there are quite specific patterns. It seems like topological defect on the periphery tend to be occupied by the small regions, and compared with monodispersed, there are more topological defect in the bi-dispersed system. And these small regions tend to connect to each other's. Yeah, we haven't further explored for now. So just make a conclusion. We plan to explore the bi-dispersed system with the least parameter partition problem, and using a particle system with long-range repulsion interaction, it seems that it provides a relatively good topological structure. And still, two questions should be answered. The first one is, for different value of error ratio, which combination of Q and N in bi-dispersed particle system can yield good topological structure? And is there a correlation between the choice of error ratio and Q and N? And a more general question is that, is there a better long-range repulsion system, or maybe a short-range repulsion system for templating the partition pattern? Okay, that's all for our research for now. Okay.
So I'm just trying to make sure I understand the thought process here. So
okay.
Step one, come up with a seed.
Yes.
Right? So you have an algorithm to try to help you find the topology of a good seed. And you have a surface evolver that will then sort of distort the lengths and stuff, trying to maintain the same area. Let's say the area ratio is 1, the same area among all the different partitions while minimizing the perimeter. Is that right?
Yeah.
Is that correct?
Yeah, I think it's correct.
So I guess I saw a lot about how you pick the seed. I didn't see a lot about the algorithm for actually minimizing the perimeter. What exactly are you doing for the perimeter minimization part?
It contains some local local search operation, T1 transition, and I don't know if it is enough for a question.
Is it Voronoi level step based, or is it just trying everything? Like, yeah, is there what's the logic behind how it actually distorts the perimeter lengths in order to try to?
It's the surface evolver from that statement. So it takes into account the pressures between neighboring cells and also minimization of the perimeter.
It's a gradient descent.
Is it gradient?
The
Okay.
Okay.
Gradient descent.
So it's constrained gradient descent, right? Okay.
Okay. Yeah. The basic method is. gradient.
So they get used for local minimum.
It would be local minimum, right? Which is why you don't know if it's global minimum.
So thank you. It's
Okay.
Very nice, interesting. Lots more questions to follow up on, but there are some of these sort of 2D Coulomb models, I guess, where you worked on your fluid and your
Yeah.
that recall.
Yeah.
You can predict the local area fraction, like how much area per particle. And can you use that information about the local density of particles to sort of help choose your size ratio for the cells that you're trying to template, or does that make you understand what I'm? There's some analytic solutions, at least for axiometric patterns of charge, where you can predict the area per particle. Is that information you guys try to use, or you just?
No, we just converted C point to the using the Voronoi partition and don't consider the area distribution.
Yeah.
So the area ratio is fixed.
Well, you want a fixed area ratio. I guess what I mean to say is there's theory,
Should we do it the other way around?
which can tell you
Yeah.
how to design your interaction parameters, your potential parameters to get an area ratio that's close to 1.4. I don't know if that's gonna give you a good initial configuration, but it's at least a way to flex with.
Is it just, is it just the perimeter that you're optimizing or minimizing, or is it perimeter to area?
It's just a parameter minimizing. Yeah.
So it's constrained. Sorry, just a question.
I guess this Coulomb interaction is built into your algorithm to avoid having trial solutions where the bubble centers would be very close, while the areas are such that they typically have to be at a certain distance from each other. Wouldn't it be interesting to have also some interaction between the C points and boundary? Because having the C points sitting on the boundary is something that would naturally not be a good guess. So it might be another interaction, pushing a little bit the C points away from the boundaries.
Oh no. Okay. So you suggest that we can put some interaction between the points and the boundary that make it a good structure. Yeah. Okay. Thank you.
At what point does it just become difficult to just enumerate combinatorially all the possible partitions of the disk that you could prove which it happens to be? Once you know you've listed all the possible combinations, you can prove which one is the least permanent partition, I guess.
So you want to know the difficulty in enumerating all the possible topological structure.
Yeah.
Why and become larger it is so difficult?
True. At what point does it become too difficult?
Okay. Actually, previous research finds that the number of candidates grows exponentially with the n. So when n equals to 10, I think it's about 100,000 or more.
Really?
Yeah.
Already by 10 gets to 100,000.
Yes. And you should also consider after you get the topological structure, you should consider whether this region is small area or large area. That makes it more complicated. Yeah.
Yeah. I seem to remember maybe 20 years ago or so, there was an interest in so-called experimental mathematics, where you would use a physical problem to help you find the optimum. So for example, this is the soap film problem.
Yeah.
So if you set up the soap film problem with your topology, and just let it go. It'll find you the minimum perimeter solution.
Have you seen?
You'd have to start it somehow. Like if you could start it out with equal areas, right? Because that area will be conserved in area, and you just let the film go, it'll find you the one that minimizes the perimeter, right?
It will be a local minimum, not necessarily.
Well, so is this, right? So it'll find it, but it'll find it in less than a second, right? So that was the idea, is you make the computer out of the physical problem rather than, so actually, it's funny you say that, because they tried to use soap film to prove that P equaled NP. Because for a while, people thought you might be able to get the global minimum, and that would be an NP hard. And then they proved that you'll never be able to, you only get local minima. But it still gets you the local minima in a fraction of a second, which is faster than a computer, right? And that's actually why they, if you ask like, why do we do quantum computing? It's because quantum mechanics is harder than classical computer. So make the computer out of quantum mechanics. Why not make the computer here out of soap film, right? Because it'll get you the answer faster than an optimizer. You could, and then you could do that up to like, you could do 1,000. If you had a good topology, you could do like 1,000 bubbles. And then just let it go and it'll find you the local minimum faster than you can evolve it.
Might be an issue with coalescence.
Oh, I'm sure there's all sorts. I'm not an experimentalist. 20 years ago, all I can say, 20 years ago, people were trying to solve these math problems with experiments.
One of the results of that, though, is that the setup time between experiments,
It's longer than the solution time.
the computer solution
I'll let
time.
the manufacturers deal with it.
Right, so you can, the individual case is very fast compared to the computer, but the computer can switch. And also you have 1,000 computers.
You're thinking it's hard to make a quantum computer?
Not a quantum computer, I was thinking about.
Well, it's the same, it's the exact same
But
problem.
also in one.
The hard thing is supercomputer.
It's hard to make a supercomputer.
Well, they're trying to make a computer using turbulence.
Yeah, yes, exactly.
Yeah, same idea. Find a problem that's hard to do on a computer and make that. computer.
Yes.
Possible to.
Until the 2000s, this experiment where they put charges in a room to find gravity in a multiplying system was the fastest way.
Yeah.
It was a physical computer.
Physical computer.
Yeah, so that was developed in the 40s.
Yeah.
Along with the visual computing.
John, more on? Well, yeah.